Okay, so let's just jump right in. We all know what a triangle is, right? It's one of the very first shapes we ever learn. But what you might not know is that hidden inside this super simple shape are these secret points, kind of like points of power that can help us solve real-world problems, like finding the fairest meeting spot, or the safest location, or even the perfect point of balance. So today, we're going to go on a quest to find it.
So, let's kick things off with a little real-world puzzle. Imagine your house, and two of your friends' houses form the 3 points of a triangle. You all want to meet up at a coffee shop that's perfectly fair. I mean, the exact same walking distance for everybody. How in the world do you find that one magical spot?
So, this first quest, it's all about fairness. We are looking for that one single point that doesn't favor any one person. And to find it, well, we're going to need a special geometric tool.
And that tool is the perpendicular bisector. Now, I know it sounds super complicated, but it's really not. Just picture a line segment, like the path between your house and a friend's house. The perpendicular bisector is just a line that slices that path exactly in half at a perfect 90-degree angle. The cool thing is, any point on this new line is the exact same distance from you as it is from your friend.
So, how do we actually use this thing? Well, it's surprisingly easy. First, you draw a perpendicular bisector for the line between you and friend A. Then, you do it again for the line between you and friend B. And where those two lines cross, that's it. That's your spot. This special meeting place has a name. It's called the circumcenter. So, here's the main takeaway. The circumcenter is the one and only spot that is equidistant from all three vertices, the corners, of the triangle. It is the geometrically perfect answer to our fair meeting place problem.
And here's where it gets really cool. This isn't just some abstract math problem for meeting up with friends. Archaeologists use this exact same idea. If they find, say, 3 stones from an ancient circular ruin, they can treat them as the corners of a triangle. By finding the circumcenter, they can figure out the original center of the entire structure and know exactly where to start digging. How cool is that?
Okay, time for quest number 2. We're still on the hunt for a special point inside a triangle, but this time we're measuring distance in a totally different way.
So, picture this. There's a triangular park, and it's surrounded by 3 paths on all sides. You want to build a fountain right in the middle. But your goal isn't to be an equal distance from the corners of the park. You want the fountain to be the same distance from each of the paths. It's a really subtle but super important difference.
For this job, we need a whole new tool. It's called the angle bisector. This is just a line that starts at one of the corners of the triangle and perfectly slices that angle into 2 smaller equal angles.
And when you draw these angle bisectors from the corners, guess what? They all meet at a single point. Just like last time. This new point is called the incenter. And this is the one spot inside the triangle that is the exact same distance from all 3 sides, which makes it the perfect, safest spot for our fountain.
Okay, so this is where people can get a little mixed up, so let's put them right next to each other. The circumcenter is all about distance to the corners, the vertices. That's our fair meeting point. The incenter, on the other hand, is all about distance to the sides, the edges. That's our safe spot in the middle. Just remember, corner versus side, that's the key.
All right, let's move on to our final quest for a special point. This one is less about distance and, well, a little more about physics. We are looking for the point of perfect balance.
Have you ever actually tried to do this? If you cut a triangle out of a piece of cardboard, there is one and only one spot where you can balance it perfectly on your fingertip or, on the tip of a pencil. That's its center of gravity. So how do we find it using geometry?
Well, we need one last tool for our toolkit, the median. A median is just a line that connects a corner, a vertex, to the exact middle of the side opposite it. Simple as that. And every triangle has 3 of them. And I bet you can guess what happens next. All 3 of those medians meet at a single point. This point is called the centroid. That's the fancy mathematical name for the center of gravity, the true balancing point of the triangle.
And what's amazing is that there's this really elegant mathematical rule behind it, called the centroid theorem. That balancing point isn't just randomly placed somewhere in the middle. It's precisely 2/3 of the way down any median if you measure from the corner. It's a perfect, totally predictable ratio every single time.
So we found all these incredible points inside triangles. But that kind of brings up a more basic question.
What are the rules that even let a triangle exist in the first place? Turns out, triangles have their own pretty strict rulebook that decides if they can even be built.
I mean, think about it. Let's say you go outside and just pick up 3 random sticks. Can you always, no matter what, form a triangle with them? Just picture it. You got a long one, a medium one, and a really, really short one. Are they always going to connect?
The answer, maybe surprisingly, is no. And the reason why is something called the triangle inequality theorem. The rule is actually pretty simple. For any triangle, if you add the lengths of any 2 sides together, that sum must be greater than the third side. So look at the first example. If your sticks are lengths 2, 2, and 5, well, is 2 plus 2 greater than 5? Nope, 4 is not greater than 5. It fails the test. You can't make a triangle. But what about 5, 6, and 7? Okay, 5 plus 6, that's 11, that's greater than 7. Check. 6 plus 7 is greater than 5. Check. And 5 plus 7 is greater than 6. Check. Since it passes all 3 tests, that one works.
Okay, one last rule, and this one is almost like the physics of how triangles move. It's called the hinge theorem. And basically, it says that if you have 2 triangles and they both have 2 sides that are the same length, the triangle with the bigger angle between those 2 sides will have a longer third side. Now, the absolute best way to get this is to just think of a swinging gate. The gate itself and the fence post, those are fixed lengths, right? As you swing the gate open, the angle at the hinge gets bigger. And what happens? Well, obviously, the opening at the other end gets wider angle, longer opposite side. That is the hinge theorem in a nutshell.
So we've hunted down 3 totally different centers of a triangle: the fair point, the safe point, and the balance point. Which, leads me to one final question to leave you with. Is it possible for these 3 points, the circumcenter, the incenter, and the centroid, to all land in the exact same spot? Is there some special, perfect kind of triangle where the point of fairness, safety, and balance are all one and the same? Something to think about.